Okay, so this is going to be a review of probability. If you have any questions, you can just put them in the chat if they're about the question I'm working on. If it's a question about something I'm not currently working on, I'm just going to ask that you save it until the end. And if you want to say hi in the chat, that would be super also, so I know who I'm talking to. Okay, so we're going to start with this problem. It says the probability a student takes Honors Algebra 2 is 40%. The probability that a student takes AP Psychology is 20%. The probability that a student takes neither Honors Algebra 2 nor AP Psychology is 48%. Fill in the representations. So we have a Venn diagram and we have a two-way table. So the first thing I'm going to do at the very bottom of my two-way table is I'm going to put 100%. Now, I know that the probability that the student takes neither class is 48, so I'm going to put over here in the complement of Honors Algebra 2 and the complement of AP Psychology, I'm going to put 48%. I'm going to call this Honors Algebra 2. I'm going to call this AP Psych, and over here I'm also going to put 48%. So I want to point something out before we go any further. If I were to take this 40% and put it here, don't write this down if you're writing a pen, and I took this 20% and I put it here, I want you to notice something. If I add up 40 plus 20 plus 48, I get 108%. So what does that tell me? That tells me that there must be 8% of the students who take both Honors Algebra 2 and AP Psychology, because when I add these up, it's more than 100%, and that's not possible. So because it adds up to 108%, I'm going to make this 8%. And now, so that my whole Honors Algebra 2 circle adds up to 40, I'm going to make this 32%. So that my whole AP Psych circle adds up to 20%, I'm going to make this 12%. So now over here in my two-way table, the intersection of AP Psychology and Honors Algebra 2 is 8%. I have 32 people who take Honors Algebra 2 but not AP Psychology. And that adds up to my 40% of all Honors Algebra 2 students, which means 60% of students don't take Honors Algebra 2. And if 48% of them also don't take AP Psych, 60 minus 48 is 12. When I add these up, and then that would be 80. There we go. So we filled in the representations. So now the question we're trying to answer is, are taking AP Psychology and Honors Algebra 2 independent events? So what I'm going to do is I'm going to start by finding the probability of taking Honors Algebra 2. And I know that that is 40%. So now what I want to do is I want to find the probability of taking Honors Algebra 2 given that I'm taking AP Psychology. Okay. So the way I'm going to do this is I'm going to create a fraction, and the denominator is going to be the probability of AP Psych. And then I want to know who takes both Honors Algebra 2 and AP Psych. I can't fit Psych, so let's go APP. All right, so how many people take AP Psych? Well, I know that 20% of the people take AP Psych. And I know the probability of Honors Algebra 2 and AP Psych is 8%. Oop, I don't know what that was. So now I'm going to divide that out. 8% divided by 20% gives me 0.4 or 40%. Now, that's exactly the same. They're exactly the same. That means knowing that someone takes AP Psych has absolutely no effect on the probability that they're taking AP or that they're taking Honors Algebra 2. So I can say because the probability of Honors Algebra 2 equals the probability of Honors Algebra 2 given AP Psych, these events are independent. Okay, that's what I'm looking for. I'm looking to see if, knowing that the second event has occurred, if this had changed, like let's say the probability of AP Psych increased, like if this was 45% and just honors algebra 2 is 40, then we would say that they are not independent. All right. So the next question we have says a box of candy contains filled chocolates. They all look the same. 6 of them are filled with caramel and 4 of them are filled with marshmallow. All right, we're looking for 4 probabilities. So we're going to say that C is that a caramel candy is selected and that M is that a marshmallow filled one is selected. Now, I want to pause at this point and say I'm not told if these events are with or without replacement. So what I have to do is I have to think about it. I'm taking candy from a box. We're going to go under the you touch it, you take it scenario. So if you take it, it's gone. So these are without replacement. So PC1 means that the probability that caramel is selected on the first selection. So that would just be 6 out of 10 or 60%. All right. So now it says the probability that caramel is selected on the second, given that caramel is selected on the first. So first off, instead of having 9 pieces of candy in the box, I'm only going to have 9. And instead of having 6 caramels, I'm only going to have 5. Because this is without replacement. Like you touch it, you take it. It's candy. That's gross to put it back. All right. So now the question for number 3 says, what is the probability that caramel is selected on the first and the intersection caramel is selected on the second? We could expand this using the multiplication rule to say probability of C1 times the probability of caramel on the second given caramel on the first. So now we're going to say caramel on the first times caramel on the second, because now there's only 5 left again. And when I multiply that across, I get 30 out of 90. Oh, that's nice, which is approximately 33%. Now we have the probability of caramel on the first and marshmallow on the second. So probability of caramel on the first times the probability of marshmallow on the second given caramel on the first. Probability of caramel on the first is 6 out of 10. Now, my denominator is going to change here because I've taken a piece of candy out of the box. There's only 9 left, but I still have 4 of them that are marshmallow. So that means it's going to be 24 out of 90 or 27%. Okay, so again, this is a situation with replacement. I'm sorry, without replacement, because once I take the candy, it's gone. So let's look at a situation that does not have, that is without replacement. So, or this with replacement. This is without replacement. You take it, it does not get replaced. So I'm getting a little tangled up here. All right, so we've got Lily and Ben are playing Trouble. If you pop a 6, I needed a dice game. I just gotta look. If you pop a 6, you get to move a pawn out of home. So I brought the Trouble game. See, remember Trouble from when you were little? And you would pop the dice and see if it happens to be a 6. We'll pop it. And now I got a 1. And then I get a 4. And then I get another 4. Ooh, 2 4s in a row. My children are extremely good at this game, even though we all can realize that these events, 1 to 6, are all equally likely. And they're also all with replacement in the sense that once I pop a 3, like I don't take it out. It doesn't, it's not like I can't pop a 3 anymore. So doing this problem is going to be a little different than the candy, even though my symbols look really similar. I mean, look, 6, popping a 6 on the first, 6 on the second, given 6 on the first. Doesn't that look an awful lot like our candy problem? But here's the deal. Candy, once I took the caramel, I was missing 1 on the second. If I go and pop a 4, or sorry, a 6, because that's what gets you out of home. Popping a 6, 1 out of 6. Regular die, 1 to 6, 1. But now if I want to go pop a second 6 in a row, pop a 6, given that I already popped a 6, it doesn't change. I don't need to worry about like taking things out here. This is what we would call with replacement, even though it's like an awkward thing to say because you don't like take the dice off and then put it back in, right? So now popping a 6, given that, or popping a 6 on the first and popping a 6 on the second, that's just going to be 1/6 times 1/6, which is going to be 1 out of 36. So now what I want to do with these two problems, with our candy problem, with our dice problem, we've established that this is a problem without, or with, I don't want to keep changing that around, replacement. In the sense that like once I pop it, it doesn't like go away. But the candy, you touch it, you take it. This is without replacement. Okay. All right, so I have one more, and then the couple of you that are here, if you have any questions, I'm happy to answer them. I have a feeling you'll be silent because pre-cal was silent yesterday. Alice notices that 60% of the people who come to her diner like coffee, 40%, 45% like tea. Assuming liking coffee is independent of liking tea. And we're going to let event C be the person likes coffee and event T be the person likes tea. So that's a really important statement. Assume liking coffee is independent of liking tea. Number 1 says, what is the probability that someone likes coffee given that they like tea? They're independent events. What does that mean? That means that liking tea is not going to affect liking coffee. It's just going to be 60%. Now, the probability of liking coffee and liking tea. Now, in the last one, now let's compare this. If we go probability of coffee, and now we do we don't need to do tea given coffee because we know they're independent events. Whereas before, maybe they were, maybe they weren't. Dice are always independent, but I just wrote it out like they weren't, just to make a point. So 0.6 times 0.45 is 27%. Now, the probability of liking coffee or liking tea. Now, we want to be careful because I have 60% of my people like coffee and I have 45% who like tea. So immediately, what do I realize? If I add these together, I have more than 100%. And I don't know I don't know anything else. So what I'm going to do is I'm going to use the general addition rule. So the probability of coffee plus the probability of tea. And then I'm going to subtract the people who like both, which I just found up here, which was quite handy. So I've got 60% of the people who like coffee plus 45% like tea minus my 27% who like both because I don't want to count them twice. So if I do that, 105 minus 27 is 78% of my customers like either tea or coffee. I have a couple of you left here. I'm out of problems. If you want to put something in the chat, I'm happy to go over it. Otherwise, I'm going to sign off. Okay, thanks for sticking in.